Okay, we're going to be talking about cases where your number of factors and then potentially also the number of levels of your factors create non-feasible situations with regard to the number of treatment combinations. And so we use fractional designs as an answer to that. I've consulted on many projects in engineering, particularly where this is of a major concern and something that comes up frequently. All right, so as I mentioned, in many situations, we have a lot of factors, things that we believe could affect your response variable, sometimes 10, 15, maybe even 20. Let's say we take the smallest case here, 10 factors. Then if there are two levels each, so it's a two series kind of design, then we would have 1,024 different treatment combinations. This becomes quite difficult. If we go up to 20 factors, it's 1 million, over 1 million. You just can't do this in almost any situation unless you're maybe a computer simulation, you could, but that would be the only case. Okay, so one good thing about factorials is we get interactions, and we know now how important interactions are with regard to understanding the effect of those factors on the response. So we know an interaction gives us information, such as the effect of factor 1 depends on what level of factor 2 you currently are at. So, for example, in factorial experiments, we talked about the degrees of freedom associated with each of those interactions. And when we have those interactions, one way our friend Gary says is that you spend your degrees of freedom, because remember, you only have a total number of degrees of freedom dependent on ultimately the number of observations for your data set, but you don't want to spend them all on these higher order interactions. So for example, a 2 to the 8 design would have 255 treatment degrees of freedom. 163 out of the 255 would be used in estimating the 4, 5, 6, 7, and 8 way interactions. That's just not efficient and kind of you want to be more thrifty, I'd say, with how you spend your degrees of freedom. So if you know that maybe certain treatment combinations are really important, you just don't even want to regard these high order interactions. And in general, I agree with Gary's opinion here. Higher order interactions are typically more small relative to the main effects of your experiment, and those other more substantive lower order, so like the two-way interactions. So I love this principle. It's fun having a textbook author who has a funny sense of humor, but when you weigh an elephant, you don't worry about his fleas. That's Gary's advice, okay? So if you think your main effects and your lower order interactions are going to be the most substantial, just don't even investigate those higher order interactions. When higher order interactions aren't small, you may have some issues. That's way beyond the subject matter of this course, and it's something that is currently getting really heavily investigated within the stat literature. So when we want to focus in on the weighing the elephant rather than all of his fleas, we want to use something that we can keep all of the important, most salient factors and just run a part of the factor design. We don't want a fully enumerated factorial design. So you think about every combination, we're not going to regard every combination. We're going to do a fraction of all of the fully enumerated factorial levels in this design. But how do we choose the fraction? What gives us some clue about what fraction to choose? Once we've chosen the fraction of the design to carry out, how do we analyze the results? It needs to be kept into account that we only assessed a fraction of the full factorial enumerations here. If we have less data, what did we lose when going to a fraction? So we may be losing some information that may be important. We want to be able to describe that. Okay, and then what did we gain by going to a fraction? These are all important questions that we'll get to. Fractional factorials are going to be smaller than the fully enumerated factorial design. And we're generally going to first we'll just focus on those main effects and then throw in some lower order interactions as well. This kind of approach makes sense in a lot of situations where the following three hold. I really like these principles that Gary laid out because I find in my experience consulting, this really rings true with what I've seen. Okay, number one, we believe many of the factors are inert, and we are simply screening to find the factors that are not inert. So especially when you have like say 10 factors, it's usually because there are all these sources of control that the experimenter is able to delineate. And they're often in laboratory settings, so like maybe a chemical process, maybe an engineering, manufacturing kind of process where you have so many factors that could be influencing the response of interest. And many of those are not going to be factors that are ultimately important. In fact, often investigators go, oh, I kind of just think that could maybe affect the response, but they have no clear theoretical reason to believe it so. It's not a major part of their research hypothesis. So this is a case where you get these like multiple factors, but you kind of wonder really how many of these are really impactful and how many are, in the words of Gary, inert. Okay. 2, we believe that any higher order interactions are going to be small. We want to ignore the fleas and weigh the elephant, right, folks? So we want to make sure we don't heed high order interactions that may even be statistically speaking impactful, but not practically speaking. So I'll have students, it's very good to be attention to detail, but this would be one time, particularly if the effect size of your high order interaction is quite small relative to the effect size of your main order interactions, where you want to ignore things, even if they are significant, and go, I'm going to rely on effect size measures here to describe my experimental outcomes. We need to shrink the design, and that may just be because we can't record everything. It's too big. And you're willing to take some risks or overlook some things to shrink. Okay, so what are those risks? We're going to be talking about that in a moment, but for right now, we need to actually define that fraction thing that we had mentioned before when we fraction these two series. We have the regular fractions that we can explore here. There are some non-regular fractions. These are what I'm going to give you here will give you enough information so you can go on to the non-regular fractions, but I'm not going to have time to cover that. So we can build half fractions, quarter fraction, eighth fractions, and so on. The shorthand is going to be the following. So if you have a half fraction, it's 2 to the k minus 1. See the relationship there? That'd be a half fraction of a 2 to the k. A quarter fraction is 2 to the k minus 2 for a quarter fraction. And in general, 2 to the k minus p gives you a p over 2th fraction, right? So keep that general rule in mind. And when I talk about fractional factorials, I will probably really emphasize, okay, what's our p here? And that p minus 2 gives you that, p over 2th fraction of the design. Usually we're looking at things like a quarter fraction or maybe an 8th fraction. I can't think of one time I've gone beyond 8 in advising. Okay, so you can go a lot of routes for generating your 2 to the k minus p design, your fractional design. In general, you want to think about the fact that you'd be confounding all 2 to the k levels of your factorial design into 2 to the p blocks. And this in effect is going to confound any differences that you would ultimately have otherwise detected in all that fully enumerated fractional factorial design. But you're only going to run one of those blocks, so you really will lose that information. And in general, you can do it this way. I'll say this. Gary gives the advice that in practice, most of the time, people don't use this method because there's an easier way. I'll call it a textbook way for generating your design. All right, so we're going to emphasize that. You choose P defining contrasts. So these will be generators, and you can think of them as the contrasts that are going to be most important for your experimental results. If you're doing this for your own experiment, you know. If you're helping somebody set one of these up, this really entails you sitting down and talking through everything with them, and figuring out what kinds of these defining contrasts you want to use as your generating set. So for one defining contrast to be called W, we either use the block with W equal 1 or the block with W equal -1. By convention, I is a column of all those ones. And so we'll either have I equal W or I equal -W. Let's stop and see an example from the text. Okay, so we'll actually get to the book example in a second because it's actually got 5 two-series factors in it. But for this one, we have 3. So this is the most basic case we would see because actually you could fully enumerate this quite reasonably in a lot of settings. But let's consider a half fractional design here. We know it's half because it's 2 to the -3. Our design effect I is going to be the interaction ABC. And this is a fraction where the interaction is always going to be 1. So notice the contrast table. We are going to have, first just look at these main effects. It's set up so that this ABC is always going to be 1, okay? In order for that to be the case, the levels for the A and the B and the C need to be multiplied, so we always get a 1 over on the right-hand side. So notice A, 1, B, -1, C, -1 gives you +1, right? Down here, or same place here, same place there. Notice this is kind of an obvious and simple design because the coefficient for A is positive, the coefficient for B is positive, the coefficient for C is positive. And then we can devise the two-way. I wish I had thought to edit this more, but you could predict what's going to happen here when we enumerate out the AC and BC two-level factors. AB is -1 because A times B is -1. AC would be positive. I'm sorry, negative. Looking at the wrong row there. And then BC would be positive. Okay, so we're always going to have this be coherent in that sense. I'm going to stop now because I'm realizing I'm up against time, but we're going to continue with this and relate it back to those incomplete block fractional factorial designs that we looked at in the last set.